All right. So one of the things that you guys are going to be using a lot is these proto boards. This is an example of one of the ones we have. Some of the ones you guys may come across is they may just be one single column. You can find some that are different sizes. They're all going to function pretty much the same, maybe with a couple of exceptions here and there as they go. But the reason that we use these is these are for prototyping. It's so you can plug components in and out and have the same connection as if they were on a printed circuit board. These give you connectivity options to connect multiple things. So on this proto board, as you guys can see, we've got a lot of wires. These are some dot matrix displays. They're programmable. These ones have memory. They're actually really cool to use. There's some things I picked up, when I was going through the program. What these have is they've got 7 inputs. They've got a clock, they've got an enable, they've got brightness indicators, all sorts of stuff. You look up in the data sheets for these guys and there's pages of stuff, information about these. What's really cool is you'll put highs and lows based on the ASCII character codes, so basically 2 4-bit numbers, and it's going to indicate which character you want to display. So this does the entire alphabet, upper and lowercase, all the numbers, and most, if not all, of the symbols that's used in writing. So these things are way cool. And they have a little enable button on them. So you can actually go through and address these guys separately through decoders and logic and that kind of stuff. Or even this guy. This is a microcontroller. This is something you guys are going to be learning about specifically in 5th semester. This was a Pinewood Derby controller track. So this would display the time. This would display places, and I had some others that I've removed, but they would display your relative speed. So for this track or whatever, if you go flying down it, however fast you go, we had it measured how long it was. It would calculate and spit out your speed. Some of the cars we had were going like 20, 30 miles an hour. The kids I was doing this for loved that feature. They thought it was the best thing ever. And that was all run off of these controllers. So now the idea behind these is you can plug and play resistors, wires, buttons, switches, anything you want to these guys to maintain connection. And how these work is each of these guys have a series of these rails. So anywhere that you have a rail that has a color indicated to it, that's going to be all connected as if it is one connection point electrically. So in this aspect, I've got this red rail connected to every single red rail on the board. So basically that means everything on that red line is connected together. So what I would normally do is I would connect the red line to my 5 volts, my positive 5 volts coming out of my power supply. The blue I would tie connected together. That would be my ground. So when you're working with digital, 5 volts is considered a high, 0 volts or ground is considered a low. So this way I had places everywhere on this board that I could just simply wire in highs and lows to wherever I needed them to be. And so now they're all connected. They all have power. You can reach anywhere on your board. You don't have to have huge, massive wires jumping across everything. The other way these guys work is if you see all these different lines. So they do have them stamped on there. It's kind of hard to see in this view, but there are numbers that run all the way from the top to the bottom. And then you have rows. These ones are indicated by letters. So A, B, C, D, E, so on and so forth. See if I can actually get this guy to zoom. There we go. So what this setup is when you're connecting to something, each one of these rows are connected together electrically. There's basically just a metal clip that sits underneath there that your wires go into, and then they hold on and make a connection. So you have 5 components that you can stick together and make one single connection. When you jump across one of these center ones, these 2 are not connected to each other, but anything in this block of 5 is connected to each other. And then same with as you go down. This row is not connected to this row, not connected to this row, and so on and so forth. There are times that your breadboard can get damaged. Do I have it on this one? Right here on my breadboard. I marked it because I fouled it up one day. those spots no longer have connection. The little clips inside are folded up and crunched out of the way, so you can't make a connection with those, especially with chips and things like that. Wires, you can still shove them in there, they're long enough. But any of these pins and stuff, they don't work. And so like these guys, that's what those guys look like. So it makes it so you can connect in. So if you were going to make a circuit, let's say just for simplicity's sake, these upcoming circuits for basic Ohm's law, you could tie in together like you have all your reds together, so they're all the positive voltage. All the blues are now your ground. You could make a connection. You take a wire from your red rail, which is going to be your positive voltage. You run a wire into this connection point. You run from this connection point a resistor down to here. And then from here, you run a wire to there. So now when you're looking at your schematic, we can even use these as for example, just to show you guys. So with these, anywhere that there's a dot or there's a connecting line, that's where those connections are be. So right here, we've actually got 3 connections on this point. So in that spot, we could have like that. So this connection here, this line would be representative of this point. So we'd have a capacitor connected to one side, the resistor and the diode coming off of those guys. So when you draw your schematics are just an organized way to look at things. One way we like to put these, and it's just kind of a convention, is the inputs are going to be on the left, your outputs are going to be on the right. You don't have to do it, but it's a good way to kind of, when you're drawing schematics and things like that, you're not actually drawing the physical locations of these guys. Because there's going to be times where you have, like this PIC right here, this computer chip. When you're drawing it in a schematic, you're going to have these legs coming across like this, and depending on what you're using, is here. So this would be like my VCC, this would be ground. So this is power in and ground to the computer chip. This is your clock. This is your, let's like data coming in. And then these are going to be your pin outs. So for example, you would have this. So depending on the code that you send into it, you hit it with a clock pulse. It's going to interpret that signal as, okay, if I get a high on A, B, C, and D, I want to turn on, let's say we have a light, a motor. We're going to engage, so this motor is going to be going clockwise. This is going to be the motor going counterclockwise, things like that, whatever the code may be. And you're going to draw them on this board, such as like this. So we have everything coming in, everything going out. But this could actually be, this pin is number 2, this pin's number 3, this pin's number 15, this one's number 7, this one's number 3, whatever it may be. So your schematic and your physical layup are going to be completely different. But just so you have an understanding that this is how we connected it physically versus what we're drawing. And that's kind of the biggest part, is to make sure all your connections are connected together. So when you're building them, physically trace it. Okay, I'm going from my power supply into my resistor, through my resistor, and then to ground. A lot of times what will happen is you'll plug this circuit in and it won't work. When they're like, well, what happened? Well, maybe what happened is you did this. That happens quite often. So for whatever reason, you may be measuring your circuit and you're like, well, this should be hooked up, connected, right? But you missed the row by one spot. Especially when you get into digital chips, because there's so many pins. Like this little guy, this little chip is, what is he, 10 to 41. So he's a 22 pin device. So he's got 11 on one side, 11 on the other. It can be really easy to jumper into the wrong wires. But with the circuits, like I said, we'll be doing for the first little bit, they're not going to be this complicated. They're not going to be that intense. They're just going to be, fairly simple. One resistor, one diode, things like that. Any questions about that? So one of the big things too is if your circuit's not working, make sure you've got power coming in, make sure your grounds are connected. Because if your ground is not connected, you are going to have absolutely nothing. A lot of times in industry, this is something that, you know, when you're building something for the first time or repairing things, this ground wire has a tendency to not get reconnected sometimes, which then shuts the whole machine down. It's great fun when you're trying to find it or it actually got taken out and never put back. So, happened on many occasions. Any questions about the breadboards and how they work? Yes? On these guys? That's just so they have it in groups of 5, just to kind of maintain with everything else. I think that when they manufactured this, they just had a punch that had 5, and so that way they just kind of kept the same pattern. But because it has this line all the way down, all of those are connected together as one connection point. Yes. Just to keep things standard. Some breadboards you'll see, they'll punch them all the way down. Every single line would have one. It just kind of depends on what the manufacturer wanted to do at that point in time. Make sense though? There you go. Hey, and I even kept recording. That's awesome. All right. So moving on to more theory. Who feels pretty comfortable with Ohm's law right now? Getting a few hands. Getting there. Like I said, Ohm's law is the bread and butter of electronics. Without it, we can't do anything. That'll be fun to watch in the video afterwards. All right, let's do this. There we go. Okay, so let's do some practice with these. Also with these, if there comes a time where I choose a color that you guys can't see, let me know. When I'm at the front, I can usually see them pretty good because it's right there. But if it does start causing issues or whatnot, let me know, and I will make sure I don't use those colors. We had a couple of them in different classes. One class couldn't see the color in the back. One class, the other, they could see the color, things like that. So just let me know if I do use something like that that you guys can't see. All right, so we have our voltage source, we have our resistor. Let's say we have 300 volts. We need to figure out how much resistance do we need to put in this line so that we only have a maximum of 10 amps. Okay, so here's kind of the thought of it. We have some motor, we have some part of our contraption we're building. We need it to not go over 10 amps. If we go over 10 amps, we're going to burn it up. So we're going to have to put some resistance in line to be able to control that. What value does that resistor need to be? Yes? 30 ohms? Okay, and how'd you get there? Okay, remember our Ohm's law. We just have to kind of cover up the one we're looking for. Okay? Now, the other question is, how much power is going to be across our resistor?
I think it's 3,000 watts.
3,000 watts? Okay, what formula are we going to use?
Power equals voltage times current.
Okay,
So Watt's law.
for Watt's law?
So 300 times
3,000 watts, or 3,000 kilowatts. That's a lot of power, okay? That's going to burn up, blow out a lot of stuff, even if it was, a speaker. But we can get devices that can handle that much power with no problem. It could be a great big huge motor we're turning. And the bigger the motors, a lot of times they take a lot more power, a lot more wattage, a lot more current to get them to run. And they have built-in cooling systems to be able to handle that kind of power. A lot of the pumps and stuff we would use at work, they would be running off of 220 power, so three-phase power, sorry. And they would have big circulating chambers in them with water that would be running through it. So in would come cold water, it'd go through the pump, get heated, get sent out to a big cooling tank on the other side of the plant. We had great big lines running everywhere for cooling water. And along the way it would get cooled down too, but they had great big evaporation tanks and ways to cool the water back down so we could keep these thousands of pumps we had running day to day. It was usually bad news when they shut down. It was bad. Okay, so we got 3,000 or 3 kilowatts. Everybody see that? Have any problems with it? Okay. I have a resistor, and it is brown, black, green, gold. And I need to get 33 milliamps of current. What is my voltage? Okay, I'll give you guys a chance to work through that problem. Sometimes in industry, you will be given a set of parameters. You'll have a manager say, I want you to build me this, but you have to use this component. You're like, well, it'd be easier if I did some other component, but most of the time the managers are like, nope, you gotta do it this way. So, go ahead and everybody work through that. Black, then brown. For the color code. So in this, we want to find what is the voltage, and we also want to find what the resistor value is. We want to find the power, and just for practice, the max and the minimum. So I'll give you guys a few more minutes to get those extra parameters. Generally, when we're going to be doing this, most of the time you're going to be finding everything, powers, currents, voltages, across all the components. Tolerances, not necessarily every single time, but right now we're going to do it because we're going to work on both of these. And it's spinning. Okay, Fallon. Which one do you want to solve first?
I've got R1, I think.
Okay, hit me with it.
One mega ohm.
Okay, and how did you get there?
So it'd be 10 times 10 to the plus or minus 5%.
Okay, which that would shift down. We're going to increase the 5 up to a 6 to make it meg. So we got 1 mega ohm. Everybody agree with that? Okay, you're good there. Kaylee. Which part would you like to solve?
Okay, so I did the part that I'm going wrong.
Okay.
So I'm
Okay. Well, which part do you want to solve, and we'll work through it.
Okay,
So we've got R1. We have the power, voltage, resistance max, and resistance minimum. Mm-hmm. So we have 1 and 6 zeros for a resistor. So which part do you want to solve for? We've got voltage, the power, the max and the minimum of the resistor. Or are you still struggling to get that resistor value? Okay. So coming back with here, so remember our four band color code. The first two is going to be the value of our resistor. Okay. So we've got brown and black, which gives us, so it gives us 10. Then multiplied by 10 to the, which is the next color, which is green, which gives us 5. So then when we take that, basically we're trying to increase that to, we multiply that out on our calculator. We can have it display the answer to us in our engineering notation. In this case, we can either bump this up to a 6 or bump it down to a 3. Just kind of looking at it real fast. If we want to bump this one up to a 6, because that's the next closest value where we're still going to have a whole number, not a decimal. We make this value larger right here. This value is going to have to get smaller. So we're going to increase it by one number. So we're going to move our decimal place 1 to the left. So then in this case, this becomes 1.0 times 10 to the 6th. And then this part, we can convert into meg. And remembering that 10 to the 3rd is kilo, 10 to the 6th is meg, 10 to the 9th is gig, and 10 to the 12th is tera. So our resistance value we have is 1 meg or 1 million. Okay? So now let's solve for our max. So now we come back to the last band of our resistor, which is gold. And gold is 5%. So for this thing to be in tolerance, it's going to have a maximum value of this. So R1 max is equal to the value of R1 times 1.05. Because remember, 5% is 0.05. And we want to add that, and we want to get that with this original value. So that's why we add 1 to it. Yes. And then when we're doing this, we want to make sure we put that all in brackets. The one thing, too, that we want to make sure we're working through is on our calculators. Make sure you're getting these things typed in correctly. Because if you just start plugging in numbers and not putting parentheses around the values that need to stay together, it's going to start changing your answer around quite a bit, actually. So what'd you get there, Kaylee?
Okay, so it's 105 with 400.
Okay. So 10.5 meg. You agree with that? Disagree with that? 1.05? Yeah, that's what I meant. 1.05, sorry. Yep, I have my 1.05. I had my comma in the wrong spot. That makes sense. Okay. Next victim. Yes. Okay. I will get it fixed. Jeff, which part would you like to? I'll go through and make sure I have the correct spellings on these. So, you want to do voltage? Okay. What formula are we going to use to find voltage? Okay. Resistance times current. You can do that. It is a lot of volts. It is not a lot of amps. You have a lot of resistance. Okay, that's one thing to remember. Remember the relationships. High values of resistance is going to give you low current values. Okay, so if we had changed this resistor, if we plugged in, like, say, a 1K ohm, that's going to significantly jack up the amount of current. One of the cool things, though, is this voltage is not that uncommon, especially in the semiconductor industry. They have machines, like I was saying, that implanters, that they get particles and they accelerate them up. This is how they do it. They put 30,000 volts behind it, and they fire that thing. They literally, if they're firing this thing down a tube through some magnetic guide waves to kind of control where it ends up, and it just slams into the silicon wafers. There's some videos and stuff I can show you guys with those later, but it's pretty cool, and it damages the surface of the chip. Then they stick them back into an oven, and then what it does is it heats the silicon up to almost melting, or to where it almost liquefies, but it gets malleable and it heals itself, and then that ion is now part of the crystalline structure of the silicon. And then they send that off, they get it cleaned up, and then they start building more layers on it. And for the amount of doping that they need to do, it's like one particle for like a square centimeter is enough to change the electrical properties of the silicon. So they don't use a whole lot, but they slam them in there, and you can see it underneath a microscope. It looks like a crater on the surface of the wafer. All right, so the last one we got 2 left. Dylan. Yep. Minimum? Times how much? Or subtracting 5%, is that what you're saying? And it's how much? 950,000. I just don't want to write all those zeros. I'll be honest. Okay, everybody agree with that? Which one?
959.959.
Yes, that's also acceptable. Again, just look at how the answer wants it. If I was writing these out to compare the numbers, I would probably put everything in terms of meg. That way you can quickly look at it and see the distinction and don't have to convert anything in your head. Okay, last one for power. Simon, not here. Okay, Jameson. Power for 500.
The formula for power is power equals current divided by voltage. So the voltage of this equation is 33,000, and current is 33 milliamps. So multiplying those out, I get a total of 1,089 watts.
Does that sound right to everybody else? Okay, that's what I got. In this instance, like I said, going back and forth, for me, I would probably turn it in terms of kilowatts, just because 1,000 watts looks funny to me, but it's one more digit that you have to write. But either way, it's still the right answer. Okay, any questions with that? Pretty easy? We're going to go with a... Okay, so there's our circuit. We've got 9 volts. We've got a resistor, and its color code is white, brown, brown, silver. I want to know what our current total is, what the value for R1 is, the power for R1, and then I want to know what our current's going to do at the ends of the spectrum for the tolerance of our resistor value. Because sometimes we need to know that. Because when we're building a circuit, we need to know if things are going to change. If I swap this component in and out, it has the potential to be plus and minus this range. So what is my power going to do at these two different points? Correct. Because like I said, unfortunately, there's going to be times when you're swapping parts in and out. You're never going to get the same resistance value, or very rarely, of one you pull out to one you put in, even though they came from the same batch. There's going to be variances in them, even if they're ever so slight, they're going to be changing. We need to make sure we account for that in our design. Man, these new batteries are phenomenal. And then also, once we have those currents, let's calculate the powers at each of those points as well, because that's what the important thing is will this resistor handle it on either end? Give everybody a couple more minutes. have people show up today. Oh, they're showing up at 2. Okay. Alrighty. Jameson.
Current, so we found through dividing voltage by resistance.
Okay.
That's all resistance first.
Yeah, let's solve resistance first.
So white is 9, brown is 1, and brown is 0, so 10 to 1. So it gives a total of 910. Large silver band of 10%.
Okay. 910 ohms plus or minus 10%. Everybody good with that one? Okay. Let's have yourself current for their resistance, because that one we needed to get first. Alrighty. That. Okay. Current is just voltage divided by resistance. 9 volts divided by 910 ohms gives us 9.89 milliamps. Make sense? Everybody good with that? Okay. Zach. What'd you get?
89.01 milliwatts.
Okay. Agree, disagree with that value? Agree? Okay, so do I. So the Spencer. Come on. Let's get a couple of these out of the way. Okay. Spencer.
So for the maximum current, I divided the voltage by the max current, which the max current I got 1,001 ohms.
How much?
1,000.
1001. How does everybody feel about that? We good? Okay, I agree. Guess I can do it from the front. I have to keep walking over here. Morgan, use up. Power. You want to do the minimum?
Hold on.
It's up to you. We had solved for that one. I just put the wrong prefix in there. So we either want to do power for the max or we want to do current for the minimum.
I'll do current for minimum.
Okay. Okay, what formula did you use?
So I did 9 joules divided by 819.
And how many did you say? 819?
Yeah. And then I got 10.989 joules.
See, for a max, I'm looking at a little different value. I got those flipped. Okay, what's this one supposed to be? 9 divided by 1001. 8.99. So I think probably what it was is just thinking both of them in your head at the same time and putting the wrong number. Yes, yeah. Like I said, for this was, yeah, it was close, and I didn't catch it. Like I said, I did the same thing you probably did, have the two different numbers stuck in my head and just threw the wrong one in. So yes, I've got it written down correctly. Yes, so for the max, so if we have the most amount of resistance, we're going to have the least amount of current, which we should see in the difference of these guys. So the max current we have is 8.991 milliamps. When we get to our minimum resistance value, we're going to have the most current, so 10.989 milliamps. So the last one we have is the power, or the last two is the powers for these guys. So first one we're going to do is power for the max, and that's going to be Simon again. Man, nobody's freaking out so bad that their name doesn't get called. It makes me sad. That coal, might read it. They will get added back, don't worry. This will just speed things up. That would be more fun is to have them sorted because then you'd see how bigger sections. So Zach, you'll have power for the max. And just get this out of the way. Yep. And then Reed, you'll have power for the minimum. Okay? So we have power for R1 at its max point, power for R1 at its minimum point. Okay, Zach?
So I had 80.91 milliwatts.
And what formula do you use?
I used the current max voltage.
Okay, so your values were 8.991 milli multiplied by 9 volts. Okay? Agree? We good there? Okay, and then Reed for the minimum.
I multiplied my current minimum with 10.5 milliamps. So I just multiplied 10.9 times 10 to the negative 3. Multiply that by 9.
You're good.
And I got 98.1 milliwatts.
Okay, yes.
So obviously if you're taking like the different numbers, so like current max times volts max is going to have different results than like current max times the regular volts. Would that the difference between those, would that still be within the barrier?
Yeah, it's still within tolerance. So one of the things too is this voltage, even though I put voltage max, the most you're ever going to have on this one is 9 volts because there's only one component. So this is if we're taking that component out and we're putting in a different one with a different value. That voltage is always going to stay the same, but it will change once we start adding more components into it. And that'll be something we'll talk about here shortly. But yeah, you'll still be well within the 5%, the 5% tolerance.
So the like correct way would be to do the max number for both of them?
Yeah. So in this case, the maximum is going to be 9. The minimum is going to be 9. So in this case, yes, they're going to be the same. But when we start adding multiple components to it, then we're going to have to make sure we very carefully label and use the correct values. So, any questions about this? Like I said, this kind of seems like a lot of tedious work, but the idea behind it is because, for one, we have resistors that aren't going to be perfect every single time unless you pay for them. The difference being, if we could get a resistor that was 910 ohms plus or minus 0.01% if we really wanted to. So that means out of this batch, every single resistor we grab is going to be 910 ohms with a very small degree of variability. We're going to pay 30 cents for that resistor versus these guys that are 10%, we're going to pay 2 cents. And sometimes, it doesn't seem like a whole lot. We're dealing with a difference of 28 cents, okay? But when you're using these things by the thousands, that 28 cents adds up for every single component. You know, even at that, so you take 28 cents, you say you manufacture 1,000,000 units, that's a difference of $280,000. So, yeah, so this is where supply and demand, and then, you know, keeping track of the parts you use. Sure, you could use a resistor, that's precision. You really could. But you're not going to be there. You know, it's not, you're going to be eating up your cost margins, things like that. That's $900,000 or $280,000 of profit you could have made if it doesn't have to be so precise. That make sense? That's one of the things we'll be talking about a lot is when we get into these is the cost differences. Because there are times where it just doesn't matter. If you're making one or two, who cares if you use a 30-cent part or if you use a 15-cent part? For onesie twosies, doesn't matter. For big operations, that's when it starts to matter. Okay, any questions about this? Yes.
So student orientation,
Yep.
and I'm gonna pretend like I'm part of that while I'm going to bottle.
Bottle of Corona juice. Any questions? Yes.
So if you use a 80-watt resistor on this,
Yeah. An eighth watt would be good because it'd give you 125 milliwatts of power.
so that's all that you're doing, like the first picking up power of the side you're using.
Correct. Yep, that's the biggest thing is understanding. Because here, in this situation, it doesn't matter. We can plug in the one resistor and we don't have to change it. But sometimes it's going to matter because this is going to start creeping up and getting over 125 milliwatts, or it could go over 250 watts, and then we have to get a bigger resistor, which is additional costs. So, anyway, I'm going to give these guys a break. Is that okay? Hang out for about 5 minutes. Okay. So we got some guys coming in for to give you guys some new student orientation, some information about things on campus for you guys. So let's go ahead and take a quick 5-minute break, and then we'll come back and have these guys present to you and do their thing.
Thank you.
Yep.